Hey, George, you're a scientist.
I'm a chemist, yes.
Yeah, so you're a scientist. In all the time you've been sciencing professionally, because we don't count amateur science as professional
No.
science.
Yeah.
In all the time that you've been sciencing professionally, what's the most dangerous thing you personally have ever worked with?
Damn it, Lions, I'm a chemist, not a chemist. It's a chemistry one. All right, we did it. Everybody sign off, go home. So yes, I guess being a professional scientist would mean I was being paid to be a scientist, right? So
Yeah, I think that's the colloquial definition. I don't know where that
Right.
originally came from.
so this wouldn't be when I accidentally made mustard gas. Like it wouldn't be that, right? Because I wasn't getting paid to do that.
No, and
It's not
I
professional.
like to hope that you've done something considerably more dangerous in your professional career, because that was citizen jackassery. Like that was
Yeah.
that was accessible to like some kid in his house.
Yeah, exactly. No, this is professional. So there's two things. When I thought about this question, there were kind of two ways I approached it, which is like, what is the most dangerous thing, kind of period, like full stop, versus what is the most dangerous thing with like the least amount of safety guards, like the thing most likely to actually hurt you. You know, because like
Oh yeah, right. Like this thing, if this button got pushed, we would all die. But it's impossible to push the button. Is arguably not that dangerous.
yes, but like if you push the button, everybody does die, right?
Right.
You know,
Yeah.
so.
No, I
'Cause I think
like that distinction.
Yeah, because I think they're both interesting things to discuss. So the most dangerous safe thing is what we call an ICP OES instrument. And so ICP stands for inductively coupled plasma.
Not insane clown posse.
It might be.
Just because that would also be super dangerous.
I gotta say, ICP versus Inclane Clown Posse, I think ICP wins. Inductively coupled plasma. Because there can be infinite inductively coupled plasma. There is only, what, 3 clowns? Something like that?
I think 2.
I don't know.
Violent J and the other one. I don't know why I even know that.
So basically, an ICP, through the magic of science, because I honest to God have forgotten how this works. They explained it to me in college, and I was like, magic, got it. It is so basically what it's used to do is it's used to analyze for heavy metals, which I think is kind of cool because it does this by the same concept as the way fireworks work, right? Which is you put, so what you do is you get a sample, you put a whole bunch of acids in it to digest it within an inch of its life, right? So, and you heat the acids. That's one of the fun things too, is that like not only do you put acids in it, like concentrated nitric and concentrated hydrochloric, right, to make aqua regia, which is I think it's royal metal, right? Yeah. So
I love that on the way to the thing you think is actually dangerous is like quantities of very, very powerful acid, and you're like, yeah, it's the acid, whatever.
Yeah. We heat the acid up to 95 degrees Celsius.
So
just
boiling
below boiling
acid.
Yeah. Well, I mean, to be fair, it just boils water. The acid can get a little bit hotter.
Oh, good. Yeah, because you wouldn't want to vaporize it. That would be bad.
Yeah. No. And then you put a little cap on it to make it reflux, which is, literally the word. So that way it like boils up and then like kind of like drips down off the sides, so you reflux it. Anyways, so what that does is make sure that the metal is by itself. So any complexes that it's in, you've dissolved all of those complexes, right?
Because the acid will get rid of the other crap, but it doesn't react with the metal.
Well, it does react with the metal, but it puts it back into its elemental form, So,
sure. Okay.
Yeah. So basically, like it's what the acid does. I mean, it kind of does this to all things in principle, right? Is that like it's the person coming through at the dance party, right? Saying like, leave room for Jesus, right? Like it's going through and like cutting the bonds, but it doesn't tear apart the atom because like then
that would be bad.
You'd be dealing with fission material, and that's is also dangerous. So all of this is true. So basically, then what you do is the machine kind of sips it, and it shoots it through like an aspirator, so kind of like creates or a nebulizer, right? So it creates this nebulous gas, which then gets hit by the torch, which is the actual inductively coupled plasma, which then excites the molecule. And when the electrons go back down,
the word excites there is just doing a lot of like lampshading of what is actually happening.
Yeah, no, those molecules get really excited to be lit on fire. But when the electrons come back down, they release light of a very specific wavelength, and the intensity of that wavelength is proportional to the number of excited electrons. And so then you can say like, oh, there's like a bunch of cadmium or chromium because look at all this blue light, green light, red light, whatever. So that's what that is. The inductively coupled plasma itself gets up to 7,000 degrees Kelvin. You got to make sure it burns it all away.
Yeah, let me just check real quick here. That's
hotter than the surface
really
of the sun.
Hot? Like
yes,
really hot. Yes. Okay. I just wanted to make sure. Like I was thinking that sounds hot, but maybe it's really hot. I think it's really hot.
I believe that in the Oxford English Dictionary, really hot is classified as greater than or equal to the surface temperature of the sun, which this is, because the sun only clocks in at 5,772 Kelvin, like a peasant. The ICP, on the other hand, gets up to 7,000 Kelvin, which is hot. So, but... But, you know, I mean, like, I can't get to the torch. It's, like, heavily shielded, you know, and, like, you're not going to, like, go waving that thing around the lab, right? You know, like, it's...
Okay. I have some scale questions. So,
yeah.
So, the torch is inside the machine, or is it the machine? Like, can the torch be separated from the machine it's in?
The torch can be separated from the machine it's in, yes.
So waving it around the lab is not literally impossible.
All of the stuff that lets it torch is in the machine. So like you can remove the torch, but then like it doesn't have access to the argon that it needs in order to torch.
Right.
You know?
So this would be like having the handle of a blowtorch, but with like no propane tank.
Right. Yeah.
Okay.
Yeah.
So that's good. That feels like an important safety measure.
Yep.
Is this thing firing constantly, right? Like, because I'm imagining things on like a human scale that is like scrutable to me, right? So is this a thing where like, oh yes, the torch gets insanely hot. Sorry, I want to be accurate. It gets really hot.
Really hot, yes.
Really hot. But is it like, is the plasma jet, is that the right term for that?
We just call it the plasma, but
okay. Yeah. So is the plasma that it emits, is it like, you know, a micron wide for a nanosecond, or is this like, if you were looking in, could you see like, there it is, like I'm looking at like a lit up light bulb?
If you were looking in, you could absolutely see it. And I know because on some of the older ICPs, they actually used to have a window that you could look in to see it, to make sure it was on. So it is definitely seeable. The window was heavily tinted because if you look at it directly, it will burn your retinas.
Yeah.
So
yeah, because it is, as we mentioned, really hot.
Really hot. Yes. So like I said, like that is probably the most dangerous thing like that I'm around, but it's just kind of like being at the zoo and being like, yeah, there's a bunch of tigers around, but they're in cages and I'm not in a horror movie. So, you know, like it's probably okay. Right. So a lot of safety precautions around that one. This next one, there are a lot of safety things around it, but they're more administrative, not engineering. Right. So like, you know, you are taught how to handle this thing. You are taught that it is very important.
Oh, right. It's rules protecting you, not physics.
Correct. Yeah. There's PPE. There's like a bunch of different things you have to do, but you could just ignore all of that and dump it on your head and call it a day, you know? I wouldn't recommend it, but you know, you could, which is hydrofluoric acid. So
hydrofluoric acid.
Yes.
And the one that's in our stomachs is
hydrochloric, if I remember correctly.
Yeah, I think that's right. So they sound similar, but something tells me based on the framing of how this is coming up in conversation, they're super different.
They are super different. And this is the thing that I love about chemistry is that it just, you know, you can't take things in isolation. So like sodium metal, for example, right? Metallic sodium, like if you put that into water, it will react violently, creating sodium hydroxide. And I believe sodium will do it. I know potassium will, but it will react so violently that it will ignite the hydrogen it's giving off and catch fire in water.
So it is lighting the water on fire.
Pretty much, yeah.
Like it's breaking the bonds of the hydrogen and oxygen and igniting the hydrogen.
Yes. Yeah.
Yes. Cool.
Yeah. And then chlorine gas is mustard gas, which we used in, World War I as a war crime, right? If you put them together, you know what you get?
What?
Table salt. And we put that on our food.
Right. Yes. Sodium chloride.
Yeah,
yes.
Exactly. Sodium chloride's fine. It's not a problem. Yeah. Each one in isolation is horrifying, right? Well, this one's the opposite, which is that, like fluorine in and of itself, right? And it's not horrible. And I mean, hydrogen, right? So one of the things that you need to first understand is this, what is the strength of an acid, right? So you've heard of like strong acids versus weak acids, right? So the, and this is what I find fascinating about this particular chemical is that like, the way that you measure the strength of acid is in pKa, right? So the lower the pKa, the more likely it is to donate its hydrogen, right? And that's what makes it acidic, right? So all acids have a hydrogen, like water. Water has a hydrogen, right? So it's how willing is it to give up that hydrogen to whatever.
Is that why water's on the pH scale?
Mm-hmm. Yeah.
Okay. I was never sure if that was because it actually belonged there or if it was because it was a reference as the middle between these two extremes.
Yeah, no, and it's because it is as likely to accept a hydrogen as it is to donate one. It makes it dead in the middle,
right. Which means a base would be more willing to accept a hydrogen than to donate
correct.
One. Hey.
Yep. Yeah. See, you got it. And I read recently, I thought this was fascinating, is that there are more hydrogen atoms in a single molecule of oxygen than there are stars in the solar system.
Is that a particular brand of dad science joke?
Right. I saw that and I was just like, I don't know why you'd say it like that, but I mean, you're not wrong.
That's like an SAT logic puzzle kind of thing, right? Like take this quiz to see what your IQ is.
Yeah. It's just like, I mean, okay. But anyway, so for example, acetic acid, which is a weak acid, right? Like that's, it's not citric acid. It's vinegar, right?
Mm-hmm.
Has a pKa of 4.76. Nitric acid, which is considered a strong acid, has a pKa of negative 1.4. Hydrochloric acid has a pKa of negative 7. You know what the pKa of hydrofluoric acid is?
Oh, please tell me it's 3 digits.
It's not. It's just 3.6, man. It's just right? It's just a little stronger than acetic acid. But that's not what makes it terrifying. So that's actually what makes it worse, right? Because if it was an incredibly strong acid, it would burn badly when you touched it. This doesn't. You can actually have a 50% hydrofluoric acid mixture on your skin for up to an hour before it starts to irritate you, right?
Ooh.
Yeah. So, but the problem is the fluoride, right? So fluoride is, and this is interesting. So like, if you look at a periodic table, right? When you go up and to the right on the periodic table, molecules get smaller, right? Down and to the left, they get bigger, much bigger, right?
Oh yeah. Okay. I'm trying to picture it in my mind. I got you.
Yep. So if you drop a level, molecule gets way bigger, right? So like chlorine is a big atom, right? Bromine is a big atom. Iodine's huge, right? Fluorine's tiny enough to permeate your cell membranes, and tiny enough to go in. And you know what it really loves? It loves inhibiting calcium and magnesium processes. It finds your bones and it melts them.
Oh God!
It causes, and it is the fluorine item can penetrate cell membranes, is considered calcium seeking, and it causes, and this is the quote, liquefatic necrosis.
Jesus Christ!
Yep. Liquefactive necrosis. Yeah. Yeah. Which is a partial or complete dissolution of dead tissue and transformation into a liquid viscous mass. It does that to your bones. And so part of the issue is because it is an acid, the acid does help break down some of the cell membranes and barriers that would normally keep this out, right? So the acid is just strong enough to break some stuff down to get the fluorine someplace to go, but not so strong that you will realize it and immediately wash the affected area.
So how, because I feel like in like movies, science fiction books and cartoons and stuff, like acid is often shown in, I don't know how you would describe it exactly. Like it reacts infinitely forever, right? Like there's like the little bit of acid that like the alien spits out, and it like eats a hole through the floor, then through the next floor, then through the next floor, right? Forever and ever. And it's like, I know that's a dramatization, but what would actually stop it, right? Like, can each little molecule only react with a single like carb or like calcium atom, or is it like, oh, this little bit is going to cause tremendous problems because even though it's only a thimbleful, it can dissolve like a femur?
So interestingly, what you're kind of describing is the difference between a reactant and a catalyst. So a catalyst is not consumed in the process, right? And an acid is not a catalyst; it is a reactant, right? So yeah, basically, you could draw and balance an equation to say like, okay, for every X acid atoms that I have, I can dissolve Y iron, oxidize Y iron, and so so eventually the acid will get used up. It's just there's a lot of it typically, right?
Well, and no amount of bones becoming liquid is a good amount. So it's not
like them bones solid.
Like, oh, well, we only liquefied like, a quarter's worth of this bone. And it's like that. No, the N was too much.
Yeah, exactly. Right. And that's one of the things too, that is, I always kind of found interesting about, like, to your point, right, is that the alien like spits acid and it kind of dissolves everything. Most of the time with most of the acids that you're working with, right, is if you get some acid on you inadvertently, is what happens is you're sitting there working and you scratch your hand and then you keep working and you scratch your hand and you keep working and then you're like, my hand is really irritated. Oh, I probably spilled some acid on it. And then you just wash the affected area, right? Again, like if the acid is incredibly strong, it'll start burning immediately, but it does burn, right? And so, wash the affected area. I'm trying to remember if it's like a particularly strong acid. I believe that you're supposed to neutralize it first, but fortunately, I haven't had to work. I've never had to deal with the other end of a concentrated acid spill on my person. Normally, we just would say like just go to the safety shower and shower off if you feel that you've been exposed. But so please, main takeaway from that is that for safety goggles, don't take this as like safety, how to handle acid exposure. Do whatever your company tells you to do. Because it's been a while since I had that training because I'm an administrator now.
Good disclaimer.
Yeah. I say all of that though, to say that one of the things that is particularly horrifying about like some of these stronger acids is that like, or excuse me, about the hydrofluoric acid is that the one place that is used a lot in my industry is within radiochemistry. And I said, like, I will never be a radiochemist because screw working with that. And then fate so happened that I ended up managing a radiochemistry laboratory, right? But what it's used for is in part of a process called total dissolution, which I think is kind of cool.
Which is movie.
That's yes, it's where he goes to Mars and then gets melted. So in total dissolution, basically, so the idea is the digestion process I just told you, right? The idea is that like if you put, like glass beads or, like whatever, if you put a bunch of stuff in there like dirt, right, it'll basically break apart anything that is reasonably attainable, right? Like if you were to digest it, right, it breaks apart anything that where the metal could be locked up in. Total dissolution is what basically you're saying, no. What if it's really chemically locked up? Like, let's say it's like embedded in glass or something like that. You say like, okay, well, you know what we're going to do? We're going to take this thing that nature decided was solid and we said, nah, and we're going to make it into liquid because we can do that. And I find that fascinating to be like, I don't like that that's solid and I'm going to do something about it. And then we add enough acids and horrible acids to it that we're like, okay, cool, now it's liquid. And now we can get to the radioisotopes.
Is the hurdle here that glass is super non-reactive, which is why you store things in glass generally?
Yes.
So dissolving it in an acid is hard because the glass doesn't want to react with the acid.
Yeah, well, dissolving glass in anything is difficult, but there are acids strong enough that can get the job done. Right. I believe it was it's trichlorofluoric acid, something like that. I forget which one it is, but it's it does eat glass like cotton candy. Like you just put it in the glass and it just dissolves glass. The only thing you can keep it in is a Teflon lined container.
Could you imagine if they had discovered that like in quantity before they had Teflon? Look at this thing I made. Oh God, it's eating through the floor like this alien spit.
Okay, so sorry, when you say discovered, you don't mean like in nature. I'm like, no, nature doesn't make stuff like
this.
Oh,
no, I mean
only
like
people.
in the lab. Yeah, only people are this terrible.
Yeah, absolutely. Like nature says, nah, fluoroantimonic acid. That is the name of it. Yeah.
That's kind of a fun name. I like that.
Yes. Yeah. You know, it's nice. It's horrible stuff. You know, it's one of the most extreme chemicals, but yeah, hydrofluoric acid, as I said, like I never worked with it, fortunately, directly, except for very sparingly, like in the lab. But that's the one that where if somebody's like, we're working with HF, I'm like, where can I be that's not here?
So this is, I wanted to ask you explicitly, and you just kind of answered the question fairly explicitly, but have you, like when you're in the lab where the plasma, sun surface exploder is, like,
yeah,
is there any nerves or trepidation? But if you're in the room that has the glass container, I assume, of this acid, like there's a jug. Is it?
Yep.
Is it like
it is actually? It does look like a jug. The way that they store, just so you know, the way they store these acids, the way they send them, it's properly labeled. It looks very scientific, but the jug does look like one of those XXX moonshine jugs.
Yeah, with like the tiny handle.
It does have the little tiny handle. It absolutely does. Yeah.
What is the point of that?
Well, I think that, and I don't know this for sure, but my guess is that like people used to carry, you're not supposed to carry them with that, right? Like you're absolutely not. You're supposed to carry it in a secondary Teflon container, right? But I think that like back in the day, people used to carry them like that, and then they just never got out of the habit of making them that way is my guess. But yeah, they totally come in like moonshine jugs.
I mean, if it's just a glass jug, it is probably just literally a glass jug. Like, we go to a factory that produces glass jugs, and the moonshine people shop here, and so do the bone-eating acid people.
And this is something where, like, potentially some of our listeners could educate me, because that's one of those things where it's like, it just has always been that way, and I never questioned it. I just knew that every time I'd see somebody grab it and lift it by that handle, I'd be like, stop. You know what I think that it is, now I'm thinking about it, it's probably to actually give you a place to hold it as you're pouring, so that way you can, like, get a good handle on it. You're not supposed to be like carrying
it's
it
not
like
for
that.
Transport. Yeah.
But anyways, so when I'm in the ICP room, I mean, I will sit there, like I will lean against the ICP instrument and talk to somebody. Like I don't care. Like it's not a problem at all. If somebody is working with HF in the lab, and I, for whatever reason, am in there, if they're working with HF, like I make sure that I have on my full PPE. Normally, whatever it is I need from them can wait. And secondly, like if they're working with HF and they're not wearing their proper PPE, I will immediately call them on it, because that is scary.
Oof. Well, horrifyingly, this does make me think of another question I wanted to ask you about.